Hi, in this lecture we are going to be discussing about the first machine learning algorithm called a linear regression. Regression analysis is a very popular and a very old method and a very used method when it comes to analyzing the relationship between two variables or actually multiple variables. So in a regression analysis, the goal is to build an equation. The equation where the predictor is considered the y and the outcome is considered the y and all the predictors are considered the x, and then you are trying to predict the y with the x using that equation. So it tries to estimate the value of dependent variables from independent variables using a relationship equation. The relationship equation is the model in linear regression. So when you are doing modeling in linear regression, you are trying to build nothing but an equation that explains the relationship between the dependent variable and the independent variables. The dependent here being the outcome variables and independent variables being the predictor variables. It is typically used when both the dependent and independent variables are continuous. So everything is numbers and both of them are contiguous numbers. So that is when regression analysis comes into play, where you're trying to predict a number as opposed to trying to do classification. In regression analysis, you need to always look at something called the goodness of fit, or how good the regression analysis or how good the equation explains the relationship between the predictor and the target variables. So we will see how this goodness of fit is determined and how you have to look at this goodness of fit to see to verify how good a model that this regression analysis has built. Let us start with to understand what is a linear equation. You might have already seen this kind of linear equations in your mathematics classes, either in your school or in your college. So a linear equation is something that explains the relationship between two variables with an equation. So let us consider that x is an independent variable and y is the dependent variable. You can explain the relationship between x and y using an equation called y equal to alpha x plus beta. So y is the dependent variable or the outcome variable or target variable. X is the independent variable or the predictor variable. And you can write an equation where y equal to alpha x plus b, and determining the right values for alpha and beta, you can predict y by using the values of x. Alpha is called the slope. The alpha is called the slope because alpha is equal to y by x is the formula that they typically use. Is a number, and if you look at the plot on the right side, you see that this is a line. The slope of the line is considered y by x, and the intercept of the line is beta. Beta is the value of y when x is equal to 0. So when you put x equal to 0 in this equation, the moment you put x equal to 0, the alpha into x becomes 0, so y equal to beta. So beta is the value where the line intercepts the y-axis. So these are the two. So when you do linear regression model building, you're pretty much trying to find the values of alpha and beta because you already know x. All you have to build is values of alpha and beta. Once you know the values of alpha and beta, you can determine y. So when you're building a model, the model building process goes and looks into the data and tries to come up with the values of alpha and beta. Fitting a line. So you already now seen what an equation is. Now how do we use that concept to do model building in machine learning? It's called the concept of fitting a line. So what is a fitting a line? Says here, given a scatter plot of y versus x, fit a straight line through the points so that the sum of squares of vertical distances between the points and the line is minimized. So what exactly is this particular line saying? Suppose you have two variables x and y. Let's say x is age and let us say y is weight. And then you just draw this plot and then plot these points in this graph. So the points are going to be like all over the place. The goal of fitting a line is to draw a line through the points, draw a straight line through the points such that, so what is that such that? It says try to find the distance, the vertical distance between each point and the line. Try to find the vertical distance between each point and the line. Now this distance will either be positive or negative. So square each of such of those measures. So square each of those measures and sum it up. That is called the sum of squares of vertical distances. So find the vertical distances, square them, and then sum them. So the goal is, now in this particular set of points, you can draw any line. You can draw a line like this, you can draw a line like this, line like this. You can draw the line any way you like. But the goal is to draw a line such that the sum of squares of vertical distances, the sum of the squares of vertical distances is the lowest possible value. So if you draw like 5 lines through these points and try to find the sum of squares of vertical distances, the goal is to pick up the line where the sum of squares of vertical distances is the lowest or the minimumest value. So that is how you draw a line through the points. So obviously when you say that the sum of squares of vertical distances is minimal, the line will kind of traverse through the set of points almost through the middle. That's how you will get a line there where the distance between the points and the line is minimized. So once again, draw a line through the set of points, find the vertical distance between each point and the line, and make sure that draw a line in such a way that this distance is kind of minimized. So the best line is equal to the least residuals. Residuals in linear regression is nothing but the sum of squares. The sum of squares, the vertical distance is called the residual because that is the residual thing that is not still not mapped, or what you would say the residual or the difference, the residual between because the line is actually your model and the points are the actual values. The difference between the model and the actual values are kind of the residuals. So the best line is the line where the residuals are the least. Remember that a line can be fitted through any set of points. It is not necessary that these points have to be like almost falling in a line. The points can be all over the place and you can still draw a line. The only thing is that if you do like that, if the points are all over the place, the line is not a good predictor for determining the points. So that is something we will see in the next slide. So what we find here is that this equation, the equation for this line, so the line you draw through this set of points, this line will have an EA equation where y equal to alpha x plus b. Now that equation becomes the predictor of y. That equation becomes the model by which you can use the values of x, alpha and beta to determine y. When you build a model, you're basically finding out the values of alpha and beta. Now you take this model and you have new data. The new data is going to give you x. So apply x into the model. You already have alpha and beta available in the model, and then once you have this equation, you can pretty much find what the value of y is. Goodness of fit, as we have been talking about, how do I find if the line is a good predictor of the points? You measure something called as goodness of fit, and that is a measure called R squared. R squared is a measure which is kind of the sum of the squares of, we talked about the sum of the squares of the distances. R squared is a formula further more than that, but it uses that residual value to find how good a fit a line is. So R squared is a value that goes from 0 to 1. So it has its own formula. We are not going to go into that. Typically a machine learning algorithm, when it gives out a model, will also give you the R squared for the model. So the thing is, the R squared value, the higher the value, the better is your fit. At the bottom here, you have 3 plots of 3 sets of data, and you see for each of them how is that R squared looking like. So the first one, you see the points are almost falling in a line, and this has an equation also. So y equal to 0.97 x plus 0.18, and its R square is 0.95, pretty high, very close to 1. Now the points in the second plot you see are kind of away from the line a little. They still fall in the line, but kind of wavering away, and this R squared is like 0.74. And the third one, you see that the points are all over the place, and this R squared is 0.24. So obviously it means that If the points are falling kind of almost in line, then r squared is definitely going to be higher, and this line is going to be a very good determiner or a very good model for predicting y and x and y. Because why we say this is, now if this points are going to be closer to this line, any new data that is coming in, a new value of x will also a new value of x and y will also fall almost in the same line if the training data set and the prediction data set have the same characteristics. So this when you have put that equation in place, it is going to definitely predict it at a much higher level. Then you have something in the third graph where the points are all over the place. The new point may come somewhere here or somewhere here or somewhere here. And if you predict y there, the y is again going to be not that accurate if the points themselves are going to be all over the place. In that case, a linear model will not fit. In fact, the reason why you say it's a linear model is that you should be able to fit the points in a straight line, and that is only possible if the points are already falling almost in a straight line. Remember that you can always fit a line. It doesn't need to be that the points have to be all falling in a straight line. You can always fit a line, but you have to use r squared to find out how good of a fit this particular model is. Higher correlation usually means better fit. Typically, if you look at the correlation coefficient between two variables, if the correlation coefficient is higher between the two variables and the points are if the correlation coefficient is high, r squared will also be typically high. So the moment you are doing exploratory data analysis and you see correlation coefficient being high, you can very well say that you can find one of these variables using the other by using linear regression. Then we move on to multiple regression. What is multiple regression? Where there is more than one dependent variable that is used to predict where there is more than one independent variable, or there are multiple predictors that is used to predict a dependent variable. This is mostly the use case. You will hardly have a situation where there is only one predictor variable. Typically, you have a number of predictor variable and you have one target variable. Now in that case, the equation extends itself to like this. So y equal to beta, which is the intercept is going to be still there, plus alpha 1 plus x1 plus alpha 2 plus x2. So what you see here is that alpha 1, alpha 2, alpha 3, all these ones are becoming the coefficients for each of the predictor variables. So for every predictor variable, you have a coefficient. So when you do regression, in this case, you're going to be determining the value of beta or the intercept and the coefficients for each of the predictor variables. This is most likely the use case. The only thing is that if you want to draw this on a plot, it has to be drawn on a multi-dimensional plot, not a two-dimensional plot, and it is very difficult to visualize or even draw that kind of a multi-dimensional plot if that particular thing has, let's say, 3 dimensions or 4 dimensions. The goal is still that you still want to draw a straight line through that multi-dimensional plot such that the distances are minimum, such that the r squared is high. The same process of prediction holds good as it is in a single independent variable. The same way you use r squared, same way you find alpha and beta. And remember this, when you have multiple predictors, different predictors have different level of impact on the dependent variable. So when you do correlation analysis, you will see that different independent variables, different predictor variables have different level of correlation coefficients. The higher the correlation coefficient, the higher is the impact of those independent variables on the dependent variable, and that level is usually reflected in the value of the coefficients alpha 1, alpha 2, alpha 3. The higher those will, the alpha 1, alpha 2 and alpha 3, they will determine or they will show exactly how much is that particular variable, the independent variable impacts the dependent variable. So suppose if x1 has a high impact on y, alpha would be pretty significant. If x2, let us say, doesn't have that much impact on y, alpha 2 will be something like 0.00, something like that. So when you multiply with x2, the resultant value will be a small value which does not impact the value of y significantly. Whereas if, let's say, x1 has, let's say, significant impact on y, then alpha 1 will be significantly big compared to alpha 2 and alpha 3. When you do the exercises and look at real data, you will, when you start looking at how these coefficients look like, you will get a better picture of what I'm talking about. Using linear regression for machine learning. So machine learning, this is a very popular machine learning technique for continuous data. This is one of the supervised learning techniques for predicting continuous data. The predictors and outcomes are provided as input in the training data set. So you build a training data set, you give the predictors and outcomes to the algorithm. You tell the algorithm, which one is the target, your target variable, which ones are your predictor variables. And when the data is analyzed, it comes up with a linear equation. The linear equation is nothing but the model. So that linear equation or the model that is outputted consists of the values of the coefficients for the predictor variables, the values for the intercepts, and the value for r squared. So all of them is typically outputted when you use an algorithm to do linear regression. The coefficient in intercept obviously will form the model in this case. It is these values you are going to take and apply a linear equation when new data comes in. And r squared gives you an indication of how good a model you have built. So obviously this model that you have built is used for prediction. It is typically fast for building models. Linear regression is a very old and very popular system that has been used for building models. So let us now look at a summary for linear regression. What are the advantages of using linear regression? Is that it is pretty fast. It is pretty fast in terms of building models. It has very low cost in terms of memory usage and CPU usage. It is excellent for linear relationship. The relationship between the predictors and the target is linear, which is they all fall in that straight line. It is excellent in predicting those kind of relationships. And it is relatively accurate for continuous variable. It's pretty accurate when the variables are continuous. There is no other basic algorithm that is pretty good like a linear regression. But what are the shortcomings of this algorithm? The shortcomings are that it only can be used on numeric continuous variables. It can't be used for textual data. It doesn't work that good for classes kind of data, like male female kind of data. Data has to be continuous. It cannot model nonlinear or fuzzy relationships. That's another issue with it. It cannot really model nonlinear. So it's limited by what it can model. So if the relationship is not linear, yes, you can't do that. There are other advanced regression algorithms for modeling, nonlinear relationships or quadratic relationships and stuff like that. And it is very sensitive to outliers, though that is one issue it has. For example, we saw in this plot, almost all points fall in a straight line, but suppose just one point is somewhere far away. What is that going to happen is when the one point is far away, this line will try to tilt itself to adjust and accommodate that particular outlier point. So that way it messes up the entire equation. It changes all the coordinate just because there is this one point somewhere far away and the whole line adjusts itself to accommodate that point. So it is better that you eliminate the outliers before you start building a linear regression model. And it is the oldest predictive modeling system used in a wide variety of applications. Wherever there is continuous data prediction, it has been used for quite a long time. So it is a very popular algorithm that is used for modeling continuous variables, especially when the relationship between them is linear. Thank you.